The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, now today's lecture is long and complicated, and one often asks, well, why should we approach vibration in what is an old-fashioned and computationally laborious way when there's a simpler way that is used by the quantum chemists? But I'm getting ahead of myself. Last week, we talked about rotation, and depending on what kind of a top, you can at most get the three rotational constants, A, B, and C. That gives you some information about the geometry of the molecule. It gives you both quantitative information and qualitative information, because sometimes you see that the molecule is a symmetric top, or you see that a molecule has no microwave spectrum at all because it's a spherical top or because it doesn't have a dipole moment. So you get qualitative information, and if there's a lot of atoms, three rotational constants, if you can get three rotational constants, won't be enough to determine the molecular geometry. And that's too damn bad, because that's all you get from spectroscopy. But you can do isotope shifts, or isotopic substitution, and there's a set of equations which basically tell you, if you substitute one atom at a time, it tells you how far that atom is from the center of mass of the molecule. And so using selective isotope substitutions, one can get more geometric information, but you're always going to be short. And so our concepts of functional groups, of how are molecules built out of repeated units, is really important in being able to get from spectroscopy good geometry. It's interesting because, for microwave spectroscopy, you measure these things to better than a part in a million. So you know a lot, but you don't know everything.
So is that really not enough to figure out? I mean, there can't be two different configurations that have the same rotational constants to a part in a million.
Sure there can. You can solve the geometric equations, and I mean, suppose you have, formaldehyde, for example, has two different bond lengths and and actually two angles. And so three pieces of information will not be sufficient. However, you can determine whether it's planar or not by certain properties of the spectrum. But you should not be able, from microwave spectroscopy alone, without isotopic substitution, to determine more than 3 bits of structural information.
Okay. Even if one has, from sort of heuristics, some idea, that hydrogens don't make more than one bond, and
yeah, but still, I mean, we're already assuming that the two CH bonds in formaldehyde are identical. And that's a reasonable assumption. And again, it's confirmed by the symmetry properties that appear in which transitions and where the dipole moment is. But you really can't get as much information as you do, say, from X-ray crystallography or NMR about the geometry of a molecule. You get it very accurately. You get a little bit very accurately. Okay, and so one solution is to think, well, let's go to the next step and look at vibrational spectra. And vibrational spectra also tell you nothing quantitative about geometry. They tell you qualitative things about geometry. But vibrational spectra also have problems. Vibrational spectra provide too little information to determine all of the force constants in a molecule. Just a simple little calculation will convince you if you have 3n atoms, they're going to be 3n minus 6 normal modes. And if you have, I said 3n atoms, n atoms. If you just do a simple calculation about how many bonds you will have for an n-atom molecule, as n gets moderately large, it's a lot larger than 3n minus 6. And so you can't even, from vibrational spectroscopy, determine all of the force constants. So it's beautiful spectroscopy, but it's incomplete. And that's one of the beautiful things about it, because you always want more, and you always have to figure out ways to get the little bit more that you want. And okay, so we're going to start talking about vibration of polyatomics. And I'm really, I've got 13 pages of lecture notes. And I can't possibly get through 13 pages of lecture notes. And so we'll see what we can do here. But so first of all, what do we get from a vibrational spectrum? There's a lot of qualitative information based on group theory. And one of the things you can get from the vibrational spectrum better than from the rotational spectrum, because there's more information and more possibilities that can be ruled out, you can get the point group. Now, one of the things that people in my group have begun to realize is that point groups are often a too crude concept for describing molecules, especially when the molecules are undergoing large amplitude, are floppy. They could undergo large amplitude vibrations. The point group, there's always a permutation inversion group, and there are going to be feasible and non-feasible operations. The set of feasible operations is isomorphic with a point group generally. And so this is a concept which you say, well, it's a little bit too crude, but it usually works. But so the vibrational spectrum can tell you what is the qualitative symmetry of the molecule. It can also tell you the number of vibrations of each irreducible representation. So if you know group theory, you know what an irreducible representation is. If you don't, well, too bad. There are flavors of vibration, and they have symmetry consequences. And there are 3n minus 6 flavors, and they divide themselves among the various symmetry species that are possible. And it's possible, very simply, to figure out how many of each. You can also infer bend versus stretch or other qualitative things about the vibrations using a little bit of group theory. And I love doing this, and so I probably will. So there'll be some normal modes, and some of them are predominantly bends, and some of them are predominantly stretches. And you can figure out from simple group theoretical arguments how many bends, how many stretches, and what are their irreducible representation labels. You can work out the infrared and Raman activity of the various vibrations. And this is really how you infer the point group of the molecule. And then, since one is going to be taking spectra, different normal modes and combinations and overtones will have different rotational selection rules. And you can tell from the group theory what those will be. So that's all the qualitative stuff that I can think of off the top of my head. And the quantitative stuff is, well, you get some force constants from the spectrum. Not all of them, but you get some force constants. You get you can predict the spectrum from force constants and geometry. So if you know the force constants in the geometry, you can predict the spectrum, and you can, if you know the geometry and the spectrum, you can go in the opposite direction. There are isotope effects. And there are pictures of normal modes in terms of internal coordinates. So with internal coordinates, those are bond stretches, angle bends, localized things, the way we think about the molecule. And so one can build up a picture in terms of arrows of various lengths and angles, indicating what the normal mode looks like. And those are often very informative. And one of the nicest things about the quantitative picture is you can go beyond normal modes. Because the whole point of the normal mode treatment is to build up a basis set, a complete basis set, in which we can expand, describe anything that the molecule can do. And in 2008, we're pretty sophisticated, and we're asking the molecule to do very complicated things and hoping that we can understand that from the spectrum or from simple calculations. And so my favorite things about beyond normal modes have to do with perturbations. And there are certain kinds of perturbations that are one-off. You know, you get an accidental degeneracy and you analyze it and you learn something. But mostly when you have a perturbation, you have a whole family, a whole cascade of perturbations, and those are called polyads, and one perturbation leads to a whole bunch of insight into the vibrational dynamics. And so, polyads. And so, beyond normal modes means dynamics. And not just this piddling little dynamic of shaking around equilibrium, but large amplitude motions. Are they organized or disorganized? Now, this is why I'm giving a lecture. I'm not going to cover 13 pages of lecture notes. I'm trying to give a sense of what is special about the problem. Okay, now, there are two approaches to vibrations. One approach is computationally really simple and conceptually vacuous. And that is, well, we could do what the modern quantum chemists do. Their goal is to get to the truth. They are going to calculate a number or a bunch of numbers as accurately as possible, and they're not too concerned, at least in the act of calculating, with what the numbers mean. The numbers are the numbers. So we could say, all right, here we have mass-weighted coordinates. It's just a convenience. If you mass weight, then the equations get simpler. And there's nothing all that special about it. So we have the mass of atom I. This is the displacement of atom I. And so this is the displacement, the x displacement of atom I from equilibrium weighted by the mass. And so we have 3 Cartesian displacements for each atom, 3n Cartesian displacements. So we'll have 3n of these. And the quantum chemists don't want to do a lot of thinking about this, the geometry of a particular molecule. They're going to solve, they're going to find the equilibrium structure, and then they're going to pin down all the atoms except one and displace one in x, y, and z directions and determine from infinitesimal displacements the Cartesian force constants. So we have 3n of these, and these are force constants. Or mixed second derivatives of the potential. So if you have that, if you have these things, then you can describe the potential as the sum over I and j of these force constants times the mass-weighted displacements. So since we have mass-weighted coordinates, when we take the derivatives, we're getting mass-weighted force constants. Okay, the mass is implicitly here. So anyway, we get this set. We can determine the potential. We can calculate the kinetic energy because the kinetic energy is given by the time derivatives of the coordinates, and one can solve for the vibrational normal modes. So this is described in the older edition of Bernath. I'm not sure whether anybody has the new edition of Bernath, but the one that pages 220 to 225 of Bernath tell you how to do this. So it's a straightforward thing. What you get quantum chemistry is chemically is the geometry and the force constant matrix, and you find the normal modes. Basically, you're diagonalizing some sort of an equation, and where it's a 3n dimensional problem, you get 3n normal modes or 3n frequencies. 6 are 0. Because you start with 3n force constants, and you know that there are going to be 3 translations, 3 rotations. And so those are not vibrations, and so you do the calculation correctly, you're going to get 6 zeros. Now, it doesn't really matter anymore what the dimension of the matrix is. If you're wasting a few, if you have a 20-dimensional matrix as opposed to a 26-dimensional matrix, the computer isn't going to say, I can't do that anymore. So it's a wonderful convenience to solve for the frequencies of the normal modes. And in fact, you can also do this without saying you just have harmonic potentials. You could have higher than quadratic terms in the potential. And so you get numbers. And people like numbers because they put them in tables. And that avoids thinking. So these numbers, now you solve some equations and you get eigenvectors. And these eigenvectors actually tell you what the normal modes look like. So it's not bad. You find the frequencies and you find what the normal modes look like, but at no point was there chemical insight. When you do isotopic substitution, you do it over. You have to do the problem over. Well, actually you don't, because you know what the force constants are, but you still have to solve the secular equation. There are a lot of things that you can do quickly, but without a great deal of insight. So I think there's a great deal more insight obtained by doing the old-fashioned Wilson-Decius cross F and G matrix treatment of vibrational problem. And the notes are quite explicit, and I'll cover as much of the notes as I have time for. Okay, so there are a lot of matrices involved in this and transformations involved in this treatment. But the two key matrices are called the F and G matrix. F is force constant. It's 3n minus 6 times 3n minus 6, as opposed to little f, which is what the quantum chemists use, which is 3n by 3n. And G is short for geometry, and G has all of the masses and all of the things you know about geometry in it. And these two things are sufficient to generate all of the normal mode frequencies and the displacements from equilibrium, these little arrow diagrams. So this is what these are the key actors in all of this. And what we're going to want to do is show where they come from and how we solve this problem. Now, all treatments of vibration start with classical mechanics. And one goes back and forth between classical and quantum mechanics without even realizing it, because a lot of the symbols are the same. But one of the neat things about the classical equations of motion is that they're expressed in terms of the Lagrangian as opposed to the Hamiltonian. And in the Lagrangian, you express things in terms of coordinates and velocities, and in the Hamiltonian you express things in terms of coordinates and momenta, and really pretty much the same thing, but there's an interesting minus sign that appears here rather than here. Okay, so let's begin, and let me try to avoid overwhelming you with the many, many quantities that we deal with. So our goal is we want to write the Hamiltonian as two separable so this is the kinetic energy. There are no cross terms. This is the potential energy. There are no cross terms. We want to somehow put the Hamiltonian for the nuclear displacements into this form. These are called the normal coordinates. And how do we get to them? Well, we get to them in a very laborious and tedious manner, but we get to them. So we have the displacements, and so those would be psi1, psi 3n. So there's 3 of these, and they're defined x1, x1, equilibrium, x to zn minus zn, equilibrium. So these are the simple displacements, and now we go to the mass-weighted displacements by multiplying by this mass matrix. So we want Q, that's the square root of a square matrix, multiplying this psi matrix. But this square matrix is diagonal, so the square root of a matrix in this case is just the square root of all of the diagonal elements, because there's nothing but zeros off diagonal. So that looks like m1 square root, m1 square root, m1 square root for x, y, and z for mass 1, and then finally mn square root. And then we have x1 minus x1e zn minus zn e. So this is an easy thing. So the M matrix takes you between psi and q. So what we're really interested in is internal coordinates. And those are called S. And they're not, sometimes people use the notation S for symmetry coordinates. And there's two ways to get to S. One is from the mass-weighted, did I write down what the mass-weighted ones were? I guess I did. Oh no, I skipped that. Well, where is it? Yeah, no, here, I have them. Okay, so one way is to get from the mass-weighted displacements to the internal coordinates by this D matrix, and the other is to get directly from the psi's by the B matrix. So here's a D or B. They basically do the same thing, and there is a lot of work or a lot of vector analysis in figuring out what they are. We will skip that for the time being, because the purpose of this lecture is to show that the secular equation that we want to solve involves the product of the G and the F matrices. And we have to define what the G matrix is in terms of these things. And then we start doing, it's a long, complicated bit of analysis. So we have a transformation that takes us from psi to S or from Q to S. That's not enough. We then want to have a transformation that takes us from S to the normal coordinates. So we say that L minus 1, the inverse of the L matrix, takes us from the internal displacements to the normal coordinates. So our job is going to be to determine B or D, going from one to the other is trivial, and L. And L is going to be the transformation that diagonalizes GF. But you don't know that yet. You don't even know what G is. And oh, what a stupid thing I did. I got a blackboard over here. So let me just draw a road map. We have psi, we have q, and m to the 1/2 takes us there, and we have s, and d takes us there, and then we have q, and l minus 1 takes us there. And if you want to go directly, we have b, which is equal to d times m to the 1/2. So there's a whole bunch of matrices and transformations that we're going to deal with. Okay. We're going to show today that G, the geometry matrix, is going to be given by or defined as D diagonal. Which is, you know, a kind of silly thing. You don't really know what G is, and you certainly don't know what D is, but this is going to be the relationship between them, and we're going to have a secular equation that has this form, and that's the condition for a non-trivial transformation L. So this secular equation has to be solved in order to determine L. Okay, so basically we're just going to be taking a trip through all of these equations. All right. Let's skip that. So remember, I'm going to want to separate the Hamiltonian in this way, and but let's just develop some notation. So this is still classical mechanics, but we're going to develop a notation that invites transformation to quantum mechanics and expresses everything in terms of matrix algebra. So we have Q1, Q3n. So here we have the mass-weighted displacements, and we can write this as Q1 star, whoops, Q. So, you know, everything we know how to do with bras and kets, we're just going to be symbolically representing matrix multiplications. Suppose we want a unit vector, and so that unit vector will be in the ith position. If we want then to pick out the ith component of Q, we do this, and that just gives us Qi. Okay, just as in quantum mechanics, when we have a bra and a ket, it gives us a number. And so these equations are nice, compact ways of mnemonically representing all the transformations. So whenever you have a finished symbol like that, you have a number. Okay. Suppose we want something like this, where we have S, F, S. So this would be the force constant matrix and the internal displacements. And so a symbol like this, you know immediately that's a number. And that number is a double summation because we have two matrix multiplications. And so that is sum over I and j of Si star Fij Sj. So these are values of displacements of the ith and jth internal coordinates, and this is an element of the F matrix. And so this is a number, and okay. So now, what are we going to do? This is all formal. So we're going to be manipulating these B and D matrices. And so we start by just saying, okay, we've got these things. We're going to come back to them next time and figure out what they are. So we're going to define S in terms of psi. We're going to define F by expressing V, the potential, as a function of the S's. So this is a function of 3n minus 6 internal displacements. And we're going to somehow get this F matrix, which will be given by derivatives, mixed second derivatives of V. And we're going to do some stuff. We're going to define G by expressing kinetic energy in terms of S dots. So kinetic energy is velocities in the internal displacements, and then we're going to get a secular equation, and that secular equation is going to be expressed in terms of Lagrangian T of S dot minus V of S. Remember, the Hamiltonian is T plus V, but the Lagrangian is T minus V. And that's, that always bothers me, but it always comes out to be true. It always comes out to give the right answer. And that's just because the Lagrangian equation of motion is just this. The total derivative with respect to time of the partial derivative of Lagrangian with respect to SI dot is equal to, the partial of L with respect to SI. So this is the equation of motion. And this looks like the gradient of the potential force. And this looks like the mass times velocity. And we take a derivative, so that's force is equal to mass times acceleration. This is F equals ma, but just in elegant notation. So we'll get this equation of motion, we'll get a secular equation, and we'll express that secular equation in terms of this product of matrices. And then we'll solve the secular equation, and we'll get frequencies and the transformation that diagonalizes this matrix, and that's the complete problem. So it takes a lot of algebra and stuff to do all of this. But the important thing is it's all formal. It's all expressed in terms of these two things, and one of these two things, not both. And okay, so let's begin. You don't really have to understand any of this. From this point on, it's just turning a crank. I will attempt to provide insights as needed, but every year, every time I give this lecture, and it's been 12 years since the last time I did it, it's been really hard for me to see what's going on because the equations block all view of what's really happening. But let me try, see if I can give some oh my God, overview. Okay, so we know that the mass-weighted coordinates have this form, so we can write that as little q m1/2. And now we go to the internal coordinate representation, and we say S is equal to B times psi, or D times Q. If we want the teeth internal coordinate, then we do this. And that's the same thing as T B psi. And that's the same thing as this sum, B T I, sum over I from 1 to 3n from psi I. Okay, so all of this, it's just writing stuff on the blackboard. And then we have the relationship between S and Q, and between Q and S. So now we're ready to begin. We want to write the kinetic energy and potential energy in terms of S. And so first of all, we have the potential energy, S1, S3n minus 6. And that's the same thing as this compact symbol. And that's the same thing as a power series expansion, where we have the displacements all 0, and then we have the sum over the first derivatives, partial v with respect to s sub t. And now I'm committing this crime, which is traditional in this field, to use this rather than the bar. But that's what you find in most of the books. And that's why I had to be dragged kicking and screaming to this, away from this notation. And okay, and then we throw away the higher terms. So this is the, and so then we say, okay, V of 0 is defined as 0. The bottom of the potential at 0 displacements is 0. Then we find the minimum of the potential, V, and so we want all of the first derivatives of the potential to be 0 as well for all t. Okay, so we're only going to keep the second derivatives. This is 0 by definition. This is 0 by finding the minimum. And this is all we've got left. Now, for real problems, the potential doesn't end with the quadratic terms. But for defining a basis set, that's what we do. We use or at least we generally use this quadratic term as how you define the basis. So you end up with anharmonically coupled harmonic oscillators, our old friend. Okay. So these second derivatives become the force constants. So f t t prime is going to be the second derivative of the potential with respect to st. Now, since you're lulled into sleep by this beautifully lucid lecture, suppose we have a saddle point. Well, so there's three situations. The minimum of the potential, what are the values of the second derivatives? What's their sign? Are they all positive or negative? And at a maximum, and at a saddle point, well, they're either positive or negative. At least one is going to be negative. Okay. So, but we're really interested only in the derivatives at equilibrium, and that's how we determine the elements of this force constant matrix. Okay, what time is it? Well, I can go on for a little bit longer. I keep committing this terrible crime of writing on the wrong blackboard. Okay, so we can write the potential energy as one half SFS. But S is equal to B psi. So V of psi is equal to 1/2 psi B dagger F B psi. Now, an important thing. The F matrix is 3n minus 6 by 3n minus 6 dimensional. This is 3n dimensional. This B matrix is not a square matrix. Doesn't matter. We can still evaluate this matrix product, but that's a caution, and that is also in Bernath, the F matrix, written as a lowercase f, is 3n by 3n dimensional. And so it's expressed in terms of these psi's, but it doesn't have this neat transformation that reduces the dimension. And so and often people don't distinguish between the internal coordinate force constant matrix and the full Cartesian force constant matrix.
So little f is just the stuff in the middle, B transform FB?
Yes.
Okay.
Okay, so we do similar things to the kinetic energy, and so I'm going to skip a step because it's clear in the notes and we're going to have to stop really soon. The kinetic energy gets written as S dot D minus 1 transpose D minus 1 S dot. So we're exploiting the relationship between psi and S. That's what D does. And so the kinetic energy has this form, and we just call that guy G minus 1. So we didn't know where we were going. We just have some matrices that take you from the internal, take you from the mass weight, from the Cartesian displacements to the internal coordinates. And this product of things is called G minus 1. And that's going to become one of the main actors in this whole drama. So we now have written the kinetic energy and the potential energy in simple terms, which are beautifully suited for evaluating the derivatives in the Lagrangian equation of motion, which of course I've covered up or erased. So let me just write one more equation and then call it so the Lagrangian, which is T minus V, gets written as 1/2. I guess it would have been more elegant to write it. Okay, so 1/2. The first term is the kinetic energy, and it's a sum I and j of G minus 1 I j s I dot s j dot. And then there's the potential energy, and the potential energy is F I j s I s j. So this is the Lagrangian, and then we take the partial derivatives and the total derivatives and we arrange things. And what we discover is that we can simplify the okay, I should just stop here because I'll start at this point next time, and I think it's going to take us more than 3 lectures to get through the 3 lectures that I planned for this problem, but it's silly to rush because after doing all this work, we have the Lagrangian. We're going to get a secular equation that we have to solve in order to show that there is a non-trivial transformation between the S's and the Q's. And once we have that, then everything is beautiful, and then we have to go back and figure out what these things are. And that's the main topic of the next lecture. How do we impose center of mass and angular constraints on the problem? So we'll start here. Okay? Thank you.